you do two things in a different order, you get a different answer.
I see.
Yeah. So then the last thing I want to say is for cross product, it takes two vectors and finds the perpendicular vector to both of them. And the magnitude of the cross product is equal to AB sine phi. Does anyone have a quick question about the cross product or dot product before we go on? Go ahead.
Can you please explain the cross product again? My headphones weren't working.
Yeah, the cross product is where you have two vectors and you want to find a third vector that's perpendicular to both of those two vectors. So A cross B gives a third vector that is perpendicular to both A and B. And the magnitude of the cross product is this equation.
Can you explain the right-hand rule a bit?
Right, the right-hand rule, I'll need to look at myself to, there we go, now I can see myself. So the right-hand rule says, let's say that we, there we go. Let's say that we have two vectors. I rotate my palm from vector A to vector B, and my thumb points in the direction of the two vectors that, the vector that's perpendicular to both A and B.
Would sorry to interrupt. Would two vectors have two cross products, because there could be two angles at which a cross product is perpendicular to both vectors?
You can. The short answer is no, because A cross B will always give the vector that's perpendicular to the two vectors that's pointing in one direction. B cross A will also give a vector that's perpendicular to both of them, but points in the opposite direction. The angle phi is always going to be the angle between just the two vectors A and B.
Gotcha, thank you.
You're welcome. I think I can entertain one more question before we need to move on.
Are you going to post these on Learn, or?
I won't be posting the review slides because they are directly from the PDF copy of the first lecture. I can arrange that to be posted today. Right, so in the interest of time, if you still have questions, please post them in the chat and we'll make sure that they are answered sometime over the weekend by sending out a mass email.
Matthew, can you quickly explain the dot product?
I will need to do that after the class if there are still questions, because I want to get through most of kinematics today. So in this case, hold your question or put it in the chat. Right.
Sir, the attendance Dropbox like closed.
Okay, let's try that again. So you should all see the attendance on your screen. Please enter the attendance now, and I'll close it in, we'll say 30 seconds.
Matthew, if we've already taken it, do we still have to do it again?
Yeah, just to be on the safe side. I mean, I found out that apparently showing a PowerPoint slide and taking the attendance in Drophat is apparently not commutative, because I can't do the reverse and get the same answer. Anyway, in the information I'll post on Learn, there's bound to be a discussion about what exactly it means for something to be commutative versus non-commutative.
Matthew, I have a very quick question. It's about Top Hat. So when I click on chapter 3, and it basically shows up the textbook, correct?
Yes.
Yeah, and if I go onto the PDF lectures, I will find the PDF version of the lecture that we are going to go through today.
Yeah, you will, but you don't want to look at the PDF copy. You want to look at the slides that I am preparing, that I'm going to be presenting to you right now, since that is going to include in-class voting questions, and that's going to be where you are able to get bonus marks.
So where can I find these slides?
If you go to the assigned tab, then you'll be able to click on the chapter 3 slides.
I believe it's not there. I just checked. I don't see it.
Not
The
there.
chapter
Right.
3 slides.
Well, you will see it in, I'll need to close the attendance. Now start presentation. You should be able to see it now. Or you should be able to see something that I'm presenting.
Yeah, I can see it now.
Brilliant, excellent. So to start, let's watch a quick video because, hey, who doesn't like watching videos about Usain Bolt? So what we're going to be doing is watching Usain Bolt achieve the world record of 9.58 seconds. And you see Usain Bolt is running in a straight line, and he pulls away from the pack and gets the world record. So my question is, what sort of physics goes into Usain Bolt achieving this world record?
Acceleration.
Acceleration.
Yeah, acceleration, what is?
Time, velocity,
Dynamic and
distance.
Friction.
Mechanics.
Fraction.
Momentum.
Yep,
Is-
yeah,
And resistance.
yeah, so you're all right. There's a lot of physics that goes into this. It basically all comes down to Newtonian mechanics. It deals with forces. It's going to deal with acceleration, velocity, energy, and everything that's fun like that. But for the sake of today, I want to specifically focus on the velocity, acceleration, time, and displacement. Since today's lecture is all going to be about kinematics. Kinematics is where you look at how to relate the position, velocity, and acceleration to each other. And this allows us to predict how an object will move, where it will be at a certain time, when it will arrive at a certain location, and how long it will take to cover a certain distance. This is why, you know, if you're walking along and your friend texts you and say, how long are you going to take to be here? You say, well, it will take me another 30 minutes, because you know how fast you're walking, so you can figure out how long it will take, because you also know how the distance to your friend's location. But kinematics is also related to something known as dynamics. Dynamics is the study of why objects move the way they do. In physics, we aren't really satisfied with the answer, something does this, because that's just because it does that. We don't like the answers of, well, it does it because that's why. We always want to know why it does it, and we keep asking why until we can't get any further in answering the question. And eventually, if you keep asking why, you get to the subject of cutting edge areas of research, trying to further that answer to all those why questions. So what I want to talk about now is the difference between distance and displacement. Displacement is where you have some sort of final location, some sort of initial location, and you subtract the two quantities. That difference we call the displacement. The distance is a related quantity, but there's a very big difference. The distance is the positive scalar quantity that describes the total length that an object travels, meaning that if the child travels from x0 to xf, the distance is going to be the same as the displacement. But if the child travels from x0 to xf and back to x0, the distance is going to be twice this quantity, but the displacement is going to be 0, because the final location matches up with the initial location. So here's another picture of the difference between distance and displacement. Displacement, you see, is going to be some sort of vector from the initial point A to the final point B. The distance can be some curvilinear path where what you do is you add up all the segments of that path, you integrate over the path, and that's going to be your total distance that you travel.
So Matthew, the displacement could be said to be as the total change in position that happened.
Yeah, basically it's the final position vector minus the initial position vector. Yes. Any other questions before I go on? Yeah, so D, you see, is the distance. This funny looking E is the Greek symbol sigma. That means that you just do a sum over all the terms on this side. This means this little delta is going to be essentially an infinitesimal change in this quantity x sub I, where x sub I is each individual segment along the path. So what the entire equation is saying is if you sum over each infinitesimal segment of your path, you're going to get the answer being the total distance. And if you want to know about infinitesimals, that's a calculus topic and will probably be in one of the sources that I post on Learn today or tomorrow.
If we were calculating displacement on the surface of the Earth over a really large distance, so covering a really large distance, would the displacement be curved along the circumference of the Earth, or would displacement technically be, you know, a straight, imaginary straight vector there?
Right. The displacement would normally, well, now you're working on a curved surface, which would mean that, strictly speaking, the displacement would still be a straight line from point A to point B, even if your curved path is along the surface of the Earth.
Thank you.
You're welcome. Good question. I hadn't thought of that before, so quickly had to think back to difference between curved paths along a curved surface and straight paths along a flat surface. Basically, curvature is really annoying and it's going to make your life really frustrating if you ever study general relativity. Also super interesting. But let's move on to a one of the bonus questions, one of the in-class voting questions, where what we have is actually relates to the question that you just asked, but we're on a circular pond and it has some sort of diameter, 100 meters, and circumference of 214 meters. And we want to know what the displacement is when we walk in a clockwise direction halfway around the pond to end up at the east end. So you see that you have 4 different choices that you can choose, and you have 45 seconds to answer the question. There we go. So you have 10 seconds left. If you don't know the answer, it's always good to at least pick the answer, make a guess. Well, time is up. And what we see is that most people were saying 100 meters east. So there were still a few choices for the other questions. sorry, the other answers. And the correct answer is that you are moving 100 meters east. And the reason why that's the answer is because the displacement is always going to be a vector. So because it's some sort of vector quantity, that eliminates answers C and D. So the question is then, is it 100 meters east or 157 meters east? Because displacement is always going to be the final position minus the initial position, and you walk halfway around the circle, then that means your displacement is going to have a magnitude equal to the diameter, and that's why the answer is going to be A. Are there any questions about that?
Excuse me, so I forgot asking that, is it required for us like to remember and know the equation you showed us on the previous page?
I mean, it's an extremely useful equation that if you use it enough, even if you're trying not to remember it, it's going to stick into your mind. So basically my answer to that is to remember it, you should always keep practicing with it.
Okay, thank you.
You're welcome.
Professor, I have a quick question.
Yep.
Under attendance in Top Hat, it says that there is basically 2 asks for today. I'm not sure why it says that.
It's because I opened the attendance, realized that I couldn't share another PowerPoint screen and had to close the attendance again and then reopen it afterwards. I will make sure that that first attendance is removed.
Okay, thank you.
You're welcome.
Matthew, I have a quick question.
Yep.
So do you recommend taking notes as we go through the PowerPoint or taking notes from the textbook when we go through it by ourselves?
That is completely up to you, whatever you would find the most useful. Because there are these in-class voting questions, you might find it beneficial to quickly jot down things that I'm saying, since what I'm saying isn't always going to be written on the PowerPoint slide. The PowerPoint slide is simply a guide to highlight the main topics, to remind me of what I'm saying and to remind you of the main topic when you go back and look at the PowerPoint slide.
Excuse me, just want to
Yep.
confirm, like is the distance a scalar, right?
Yes, the distance is a scalar quantity.
Okay, thank you so much.
You're welcome. So with that in mind, that actually leads us to the next in-class voting question, where we have the same situation, but now we want to know, what distance have you traveled around halfway around the pond? So we see we have the same answers, and you have another 45 seconds to answer the question.
Matthew, are we going to complete chapter 3 today fully?
That's my hope. If we don't complete it all today, we'll only have like a few extra slides to do.
Okay.
Sir, while we're waiting for everyone to send in the answers, could you re-explain the variables of the equation?
Yes, I can. Well, at least I'll have to do it. Will that? Let's send that out as an email, because I'm afraid that if I go back, I might not actually be able to go forward again without voiding everyone's responses. That's something that we'll need to make sure doesn't happen to be on the safe side, but I don't want to test that out during the middle of the lecture. So just post in chat and we'll make sure to get to it over the weekend. Right. So what we see is that the vast majority of people said 157 meters, and that is correct because we know distance is a scalar. So answers A and B are wrong. That leaves whether the answer is C or D, and distance is always the total length of the path that you travel. So if a circle has a circumference of 214 meters and you travel halfway around it, that means that you travel half the circumference, and your answer is 157 meters. So moving on to the next thing, we need to talk about speed and velocity, where what you'll see is that you can define something known as a motion diagram that tells you how an object moves at each interval of time, what exactly is happening to its velocity. So if the objects are constant at constant spacing at each interval, you know you're moving at a constant velocity. But if the spacing is increasing, that means your velocity is accelerating. Whereas if the spacing is increasing, you're undergoing some sort of deceleration. Now, in physics, we always use the term speed and velocity, but in everyday life, those are used interchangeably. But strictly speaking, speed is always going to be a scalar quantity that just represents how fast an object is moving. So if I'm walking down the road, I might say I'm walking at 3 meters per second. Okay, that would be me speed walking. But let's say I'm speed walking down the road at 3 meters per second. But velocity is a vector, so it also describes the direction of motion, meaning that I would say I'm speed walking at 10 meters per second northward. So I also need to add in where exactly I'm going. Because we have speed and velocity, we can find something known as the average speed and the average velocity. The average speed is taken to be just your change in your total distance divided by your change in time. Whereas the average velocity is taken to be the change in displacement divided by the change in time. So my question to you is this. Can you have a non-zero average speed but a zero average velocity? Yes or no? Yes. Exactly. Yeah. So the answer is yes, because displacement can be zero, but this distance need not zero. Sometimes you'll be presented with the position versus time graphs, where based on the graph, that's where you can read off what the average velocity is. The average velocity is just going to be the change in position between two times, and that's basically the slope of the line between those 2 points. You can also define something known as instantaneous velocity. That's where you look at the velocity only at a single instant in time. This is why you need to care about calculus and physics, because the way that you obtain the instantaneous velocity is by taking the derivative of the position. So the first derivative of the position is equal to the velocity. Sorry, equal to the instantaneous velocity. And you can also find something known as instantaneous speed. This is where it's just going to be the magnitude of the instantaneous velocity. So going back to our position versus time diagram, we see that we can determine the average velocity between 2 points, but the average speed, the instantaneous velocity is just going to be equal to the rate of change equal to the derivative at a single point. You can think of this as being the slope of the tangent line located at this time t. Now, reading graphs is extremely important, so I think I should stop here and entertain any questions you might have about determining average velocity or instantaneous velocity from a position versus time graph.
When we need to find the derivative to find the instantaneous velocity, will we be given an equation for the slope, or will we have to try and figure that out?
Yeah. For the derivative, you will normally be given some sort of equation that might say your position is something like a plus b times t. What is the velocity? And then you differentiate with respect to that. The slope, strictly speaking, only really comes in like you would only really need to calculate the slope if you need to determine the average velocity. For instantaneous velocity, it's much better to use the derivative because that'll immediately tell you what the answer is rather than trying to determine the slope of a tangent line, rather than trying to determine exactly rise over run.
Sorry, what I meant was the equation of the curve. Will we get an equation of the curve to be able to find the derivative, or do we have to make our own equation for the curve?
Oh, sorry, I misunderstood. Yes, you'll be given the equation for the curve if you want to find the instantaneous velocity. Another possible question might be, here's some random curve. Where is an object speeding up or slowing down? And I think that's actually going to be the topic of in another slide or two. So go ahead.
Sorry about that. Can you please explain the derivative on the back slide, the slide that was just before this one?
Yeah.
Yep.
The derivative is physically representing something known as a rate of change. It tells us how fast is the position changing with respect to time. There are rules to how to calculate the derivative, which I don't really want to get into at the current time, but that will be the subject of your tutorial on Monday, and it'll be discussed in the additional material that I'll post on Learn.
Matthew, there is one more question, I think, by Arya.
Yes, I see.
Sorry, I just forgot to put my hand down. My bad.
Thank you. Right. So, yeah, one last question.
Yeah. So how can we define the direction of the instantaneous velocity?
Yeah, so that would be given in the problem. If you're just looking off of the graph like this one, I have no idea what direction the instantaneous velocity is. I don't know whether the object is moving north, moving 30 degrees above the horizontal. That would be something that would have to be provided to you in the problem.
Okay, thank you.
Yeah.
I had a really quick question, if that's okay.
Yeah.
Just for the slide before, and I think it was sort of touched upon earlier, but could you give for the last point, the instantaneous speed is the magnitude of instantaneous velocity. Could you give like a 20-second explanation of what that means?
Let me hold on to that question since there's an example coming up, which I think is going to help clarify that.
Okay.
Oh, and here we go. Here's the example I was thinking about. Yes, so what we have is a cheetah that is going to be running towards an antelope. The cheetah is 20 meters east to the observer. The antelope is 50 meters to the east of the observer. And we know in the first 2 seconds of the attack, the cheetah is going to obey this equation for its position. And we want to do 3 things. We want to determine the cheetah's displacement, average velocity, and instantaneous velocity. So the first thing that you should always do is draw a diagram. Even if you think you can visualize it in your head, it's always good to write down exactly what the question wants you to do, since it'll get you in the habit when you have more complicated questions, when you need to do write down free body diagrams for, say, an object undergoing rotation. It's just good practice to do. So if I want to determine the cheetah's displacement, I need to determine the initial position and the final position. Well, I know my equation for the position, so I just plug in the time of 1 second and 2 seconds into the formula and into the equation, and I subtract the two quantities and I get my displacement. Now, there's a slight typo here. The displacement is a vector, meaning that there should be direction here. I will need to make note of that and adjust the slides on Top Hat and the PDF lecture. You can also determine the average velocity in this interval, where you just take the change in position divided by the change in time, and that gets you your average velocity, which would be 15 meters per second east. And finally, we can determine the instantaneous velocity. This is where you would take the derivative of your position with respect to time, and okay, apparently Top Hat is going to be like that. Got it. So let's hope that bottom, there we go. So if you take the position with respect to time, take the derivative of the position with respect to time, that's going to get you your instantaneous velocity, which by itself, just 10 meters per second, that's going to be your instantaneous speed. Once you add on the direction of east, that's going to get you your instantaneous velocity.
Matthew, can you explain third part again?
The third part?
Yes.
Yeah, so let me go back to, here's the question we had. We had some sort of position that obeys this relation, and we want to determine the instantaneous velocity at 1 second. The way we do that is we take the position and take the derivative with respect to time. And once you take the derivative with respect to time, you plug in your time of 1 second, and that's going to get you your instantaneous velocity at a time of 1 second. For how to do the derivative, that's going to be on the in the resource that I'll post today or tomorrow. Does that help clarify it? Divisions. Okay, I don't know who is talking, so one of you can ask first.
So sir, should we include the directions of the velocity or displacement in the answer?
Yes, yes. I borrowed this slide from another source, and I'll need to adjust it so that it also includes the direction.
So right now, like, it still need to be adjusted, you mean?
Yes, yes.
Okay.
I was the other person with a question and I figured it out, so don't
Oh,
worry.
good. Right. Glad you were able to figure it out. So moving on, sometimes you want to know where your object is increasing or decreasing in velocity, but you don't know the equation of your position. All you have is this diagram. But this is where derivatives come in. If some sort of a maximum for your position, that means that the slope of the tangent line is 0, meaning that the derivative is 0. So that means that your velocity is 0. If your derivative is positive, so the slope of your tangent line is positive, that means that your velocity is greater than 0. If the slope is negative, meaning that your derivative is negative, that means that the velocity is going to be less than 0.
Can you please repeat the derivative part with the slope?
Right. So The derivative is the slope of the tangent line to the curve. If the slope is 0, that means the derivative is 0. If the slope is negative, that means the derivative is negative. If the slope is positive, that means the derivative is positive. Does that help clarify your question?
Sorry, sir. X is velocity, right?
X is position.
Position.
V is going to be velocity. V sub x just means you're moving in the x direction.
How does the derivative relate to the change in velocity, whether it's increasing or decreasing?
Yeah, the derivative of the position is always going to describe the velocity. How to determine whether the velocity is increasing or decreasing, that's where you need to take the derivative with respect. You need to take the derivative of the velocity, which is what we call acceleration, which is going to be the subject in a few slides. Does that help answer your question?
Yeah.
Yeah, thank you. Good. One last question.
Yeah, quick question, sir. Like in the high school, like for the vectors like velocity, we usually an arrow at the top of the like for example V, and there's gonna be an arrow. Are we gonna do it right now?
Not really sure what you mean by arrow, like an arrow on the curve?
No. So when we do equations in high school, we always put a vector arrow above the ones that are vectors. In the
Oh, I see what you mean. Yes. That's yes, strictly speaking, that's what happens when you have a vector. The reason why there isn't a vector in this case is because we're only considering like the x component of the vector, and this particular plot is only looking at whether you are going to be increasing or decreasing in velocity, or another way, increasing or decreasing in speed. I believe that there will be questions with vectors and with the velocity vector on the assignment. Right, moving on.
Okay, thank you.
This is an important question. We want to know, we have basically two objects A and B, and they are moving at they obey this position versus time graph. Which object has the higher speed between 0 and which object has the higher average speed between 0 and 100 seconds? Object A, object B, or both objects have the same higher average speed? Right, everything's closed. We can look at the responses. Most people said the objects had the same average speed, and the answer is C. The reason is because average speed is only the change in position divided by the change in time, meaning that we only look at the final position, the initial position. The objects travel the same distance in 100 seconds. So both objects have the same average speed.
Excuse me, Does the
Yeah.
average speed only means the magnitude of average velocity?
Yeah, the average speed is not the same thing as, it's not going to be the magnitude of the average velocity. The reason is because average velocity is going to be changing displacement, whereas the average speed is going to be just the distance divided by the time. So sometimes they might be the same, but not always.
Okay, thank you so much.
You're welcome. So moving on to the next question, we're going to look at the same graph and ask which of these has the higher speed at t equals 20 seconds.
Sir.
Yep.
I think in the answers and the question, the time value is different.
Oh, that should be t equals 20 seconds. I changed that earlier today and it didn't save. Oh well, that should be t equals 20 seconds. Though the answer is not going to change. So times up, the answer, most people say object B, and the answer is object B, and that's because object B has a larger slope at that time t equals 20 seconds in comparison to object A. So this is why we want to emphasize looking at the graph and seeing is the slope bigger or smaller than another object. Moving on to the next question, we want to ask the same question, but which object has the higher average speed at 80 seconds? Object A, object B, or they both have the same speed? Right, everything is closed. Most people are saying object A, but it's about a 2/3, 1/3 split, and the answer is object A. The reason is because we have a position versus time graph, and to determine the speed / velocity, we need to look at the derivative of the curve. And we see that object A has a larger derivative, in other words, a larger slope than object B, so that's why object A has a higher speed. Now, the last in-class voting question for a while is, do the objects ever have the same speed?
Can you show the options for like the multiple choice?
Yep. Right, everything is closed, and we see that most people are saying yes, but only sometime between t equals 20 and 80 seconds, and then split between the other options. And the answer is yes, the objects do have the same speed at sometime between t equals 20 and 80 seconds. The reason is because at time equals 20 seconds, we see object B is moving faster. Time equals 80 seconds, object A is moving faster. So at some point, the two objects have to have the same speed. Another way of thinking of it comes back to the mean value theorem, where if your curve is below the x-axis at one point, above the x-axis at another point, somewhere between those 2 points, you have to cross the x-axis. So it's exactly analogous to the mean value theorem. So moving on, let's talk about acceleration. Acceleration is going to be a vector, and it's the change in the velocity divided by the change in time. That would be the average acceleration, sorry. And you would calculate it exactly the same way you would calculate average velocity, where you're looking at basically the slope of velocity versus time graph in this case. Similarly, you can define something known as the instantaneous acceleration, where now we're looking at the derivative with respect to time for the velocity. So on this graph, we see that the average velocity is just going to be the slope between 2 points, whereas the instantaneous, sorry, let me back up. The average acceleration is going to be the slope between 2 points on this velocity versus time plot, whereas the instantaneous acceleration is going to be just the derivative of the velocity versus time plot at this time t. Are there any questions about the difference between average acceleration and instantaneous acceleration?
Matthew, how do we take the derivative? I forgot.
That'll be in the practice, the references that are posted online, and it'll also be in your upcoming tutorial. I don't really want to get into how to do derivatives here because there's still a number of slides that we need to get through today.
I had another quick question. Are the average acceleration and average velocities scalar values?
Average velocity is change in displacement divided by change in time. So no, it won't be, because displacement is a vector. Similarly, average acceleration will also be a vector because it depends upon change in velocity.
Okay, so then to follow up, would the direction also be the averages of the vector directions?
Yes, it would be. This short answer is yes, it would. Well, let me back up. And I'll actually go back here. So we have velocity that has some direction. And we have this velocity that, let's say it has a different direction. The best way to do it is to write all the velocity values as vectors. And then that way you automatically get what your vector on top is going to be, which automatically encodes not just its magnitude, but also where it's going, like in what direction it's pointing.
Yeah, that makes sense. So once you do the average calculations, it also results in the average of the...
Yeah, so it automatically spit out your magnitude as well as your direction. Yeah.
Okay, thank you.
And Matthew, will the directions would always be like south or north, east or west, right? Because you can't add or subtract north and east, something like that.
Yeah, good question. I was just thinking about that, waiting for someone to ask it. Normally, you can't subtract east from north. But in that case, you should write them as vectors. So like east would point along the x-axis, north might point along the y-axis, and because you've written them as vectors, then you are able to subtract a vector, and that's going to be able to tell you that what the resultant vector is going to be. And if you subtract north from east, that's going to point southeast, assuming I did the math in my head.
Excuse me, could you repeat that? My Wi-Fi was kind of going out while you were repeating that.
Let's say that you have two vectors. One vector points east, another vector points north, and you want to subtract the two vectors. Basically, you can represent east as pointing in the x direction, north as pointing in the y direction, and because you've written them on the xy axes, then you know how to subtract vectors that way.
Okay, thank you.
Right, so let's move on.
Sir, like, so can I ask, like, when we
Can we hold on to that question?
Sure.
Yeah, there's still several slides I'll need to get through in 20 minutes.
So Matthew, will the direction be like southeast then?
In the example I gave, yes.
Yep. Okay.
Yeah. So another thing I want to talk about acceleration deals with, you're in a car, you can be accelerating in one direction, velocity can point in the same direction, but sometimes your acceleration and velocity can point in different directions. It basically just means you are speeding up or slowing down in one of the directions. So don't want to spend too much time on this slide. You can look at it or in the textbook if you have any other questions about it. Because what I want to definitely get to is an example. What we have is a racing car that obeys this equation, and we want to know change in velocity, average acceleration, and instantaneous acceleration. Well, again, I'll need to add in the specific directions, but the way that we do the change of velocity is exactly the same way as we needed to calculate the change in position for the cheat question. This is where we plug in the times into our velocity equation, subtract the two velocities, and we get an answer. The average acceleration, similarly, is going to be the change in velocity divided by the change in time, and the instantaneous acceleration is going to be your derivative of your velocity with respect to time, and at the very end you plug in your time of well, whatever time you need, whether it's 1 second or whether it's 2 seconds or 3 seconds.
Matthew, I have a quick question.
Yep.
So in like the first equation there that you showed, like for number 1, is it, I was just a little bit confused on how we added like the 60 meters per second and then the 0.5 meters per second cubed. Like, is there any unit different? Like,
yeah, good question. So on the face of it, it looks like, well, we have meters per second here, but meters per second cubed there. And that's going to seemingly contradict everything I said at the very beginning of class about making sure units are the same. But we also have this t squared right here. This t squared has units of seconds, meaning that meters per second cubed times seconds squared still gives us our units of meters per second.
all right, thank you so much.
You're welcome.
Matthew, can you please explain the last one?
Yeah, so to determine the instantaneous acceleration, we need to take the derivative of the velocity with respect to time. And the way we do that is the derivative with respect to a constant is 0. Derivative with respect to t squared is going to be 2t. And that gets us the answer of 1 meter per second cubed times time. More details on how to do derivatives will be in the resources that I'll post on Learn later today or tomorrow. Right, Don't think I have time to talk about answer any other questions, and what I want to get into is more position versus time plots. Let's say that we have this really weird looking position versus time graph, and what we can do is look at the slope in each individual segment of the plot, and we see that it's going to be changing, it's going to be increasing, then becomes a constant. And the way that we do it is to determine the velocity, we take the derivative of the position with respect to time. So if we do that, we notice that we get a velocity versus time graph of this if we take the derivative at each point and plot the equation.
The position is just the distance, right?
Yep. Well, it's related to the distance and displacement. Position is basically like just your location of where you are. It's only when you subtract positions from each other or add positions that's when you get your distance or displacement. So not hearing any questions, you can still see this slide in the PDF lecture, but what we see is that each time there's going to be a change in your derivative, each time there's going to be a change in your velocity, that's going to match up to what your position versus time graph is doing. So as I mentioned, to go from position versus time to velocity versus time, what you do is you take the derivative with respect to time. Now, let's say that you want to determine acceleration versus time. Well, you just do the same thing. You take the derivative of the velocity with respect to time, and that gets you your acceleration, which another way of saying it is the second derivative of your position with respect to time. And we see that at each interval, if you know what your position versus time graph looks like, that automatically tells you what your velocity versus time graph looks like, which is going to automatically tell you what your acceleration versus time graph is going to look like.
Matthew, how do we do the curves for the derivative?
That's going to be talked more about in your calculus class. It'll also be in the sources that I'll post on Learn, and it also comes down from just practice knowing that, okay, if you have some sort of quadratic curve, that gets you a linear curve for your velocity, which gets you a constant for your position, for your acceleration, sorry.
Excuse me, Professor Robbins, I was just wondering, just because we're really low on time, do you think you can just wait till the end to answer all the questions so we can get us through as much as we can?
I can try that. Let's see. I can skip that. Oh, good. We're close to where I wanted to be. The one thing that I wasn't sure we'd be able to get to is relative motion. That can easily be discussed on Wednesday without any deviation from the schedule. So let's see, what was I going to say? Yes. Let's say that you have some sort of acceleration versus time graph, and the acceleration is going to be constant. To get your velocity, that is going to be your integral of acceleration, which another way of putting that is going to be the area under your acceleration curve. So what we do is if we integrate acceleration, we get this equation where we see that looking at it, the area is just going to be a square, and the area of the square is base times height. So this is what this term represents. This exotherm just comes from essentially whatever your initial velocity is. It's some additional term that you need to add on to know how your velocity is going to, what your velocity is going to be at some time t. This just describes whatever your initial velocity is. Now, let's say that we have a velocity versus time plot. The integral of the velocity versus time plot is going to be your position. Well, what we see is that the area under this curve can be broken up into a square and a triangle. Well, velocity times time, that gets us the area of this square, which is going to be this term. Then we have this second term describing the area of a triangle. Now, area of a triangle is equal to half base times height. Well, we have the half present, but the AT squared doesn't really look like a base times height term. But velocity is equal to just acceleration times time. So that gets us essentially one of the sides of the square, one of the sides of the triangle, whereas time will get us the other side of the triangle. So that's why, that's one way of thinking how you can get position out from a velocity versus time graph. You look at the area under the curve, and what you see is you get some term that depends upon the initial position plus the area of this square plus the area of this triangle. There we go. Now there's a few, we've seen a couple formulas so far. We saw this formula, which you would have also seen in high school, and we've also seen this formula, which you would have again also seen in high school. Well, what you can do is to combine these two formulas. If you take this formula and you want to, well, essentially split up this term into two copies, so you have half VI t plus half VI t, well, you can combine this term into something that looks like this, which, hey, looks exactly like this term up here, meaning that once you simplify it, you can also represent position in another way, even if you don't know what the acceleration is. Another way of getting another formula is, let's say that you have this equation, you solve it for time, and what you want to do is to take this equation and plug in your new equation that you solved for time. Another way of putting it is that you basically take this equation and apply this formula twice. If you do that, then you can get another equation that combines position, velocity, and acceleration, even if you don't know anything about the time. So to summarize, I thought I'd include this slide, and I'm pretty sure I'm on track. We have 4 basic equations for what an object is going to be doing in kinematics if we have constant acceleration. And we see that this equation doesn't include distance. This equation doesn't include the final velocity. This equation doesn't include time. And this equation doesn't include acceleration. What this means is that you don't need to know all of velocity, initial and final velocity, position, acceleration, distance, and time. All you need to know is 3 of them, and you can solve any kinematics equation that we throw at you for constant acceleration. So I want to do another, I'll do another in-class voting question where we have a situation. A marble is thrown from a very tall building. So dropped from the top of a very tall building, another marble is thrown downwards with some sort of initial speed. And what I want you to remember is these sort of equations. So maybe you want to take a screenshot or jot them down because hint, hint, you might need to use one of them. So I'll wait for a couple seconds for you to do that.
All right, thanks.
Okay, sounds good. So the question is, how does the vertical distance between the two marbles change with time? So we have 4 situations: either increases, decreases, distance is constant, or distance is 0.
Were they thrown down at the same time?
Yes, they are.
Are we assuming there's no air resistance?
Always assume that. Right, so going to the responses, it was evenly split between the distance between them being constant and the distance between them increasing. And the answer is the distance between them increases. And the reason is because, let's see if the whiteboard works. We have, oh, need to click that. We have color, red. We have a formula. X is equal to basically V naught T plus half AT squared. And we see that for an object that has an initial velocity, this term is not going to be 0. For an object without an initial velocity, this term is going to be 0. But if an object has an initial velocity, that means that after 1 second, this term is v naught. After 2 seconds, it's 2v naught. After 3 seconds, it's 3v naught. And that's why the distance between them is always going to be increasing, because this term is always going to be contributing to one of the marbles, the marble that has the initial velocity, but won't be contributing to the other marble. So let's go to the next topic. And let's say that we have a motorcycle with constant acceleration. This should be provided to you. So in the interest of time, I want to go on to this other example question, since it's slightly more complicated. So what we want to know is, well, in the interest of time, let's talk about free fall, since I really want to get to relative motion. Let's say that we have an object that is just under the influence of gravity, and in that case, we say that the object is undergoing free fall. What this means is that only gravity is pulling the object down and nothing else is causing the object to, there's no other force present. And because it's under free fall, the velocity change is the same in each instant of time. So that means that the acceleration is going to be constant, since we're only worrying about the acceleration due to gravity. So let's say that we have some sort of freely falling coin. We can describe how the coin falls by basically using our kinematic equations. If we just drop the coin, we plug in the acceleration due to gravity, divide by 2 from our kinematic equation, and plug in whatever our time is. And we see what the velocity and the position of each coin, what the velocity and position of the coin is going to be at each interval of time. Now, what I want to emphasize and what you would have seen in high school is that the acceleration due to gravity is 9.8 meters per second squared, and that's in the absence of air resistance. In general, you can always assume no air resistance because, hey, physicists like frictionless vacuums and treating things as spheres, which is a very nerdy joke that I might come back to at a later time. But basically, what we see is that if we have our full kinematic equations, we have some sort of initial position, plus some sort of term that depends upon the initial velocity, plus this term that depends on how the object is accelerating. Which means that if we just drop the coin, the initial velocity is going to be 0. If we treat y naught as equal to 0, all we're left with is this term. What I want to emphasize is that there's a minus g here for the acceleration, and that's because we are treating the downwards direction as being the negative direction. And if we have our velocity term, that's equal to just v naught plus half at squared. If we have some sort of zero velocity, all that we're left with for the velocity term is just something that depends upon the acceleration. So that's why we can say after 1 second, the object has fallen 4.9 meters with this velocity. After 3 seconds, it's fallen 44 meters with a velocity of 29 meters per second downwards. Now, I know it's 11:50. I'll just say a couple other things about free fall. Let's say that you throw an object upwards in the air. In this case, we still say that it's undergoing free fall, and that's because gravity is the only force acting on the object. It's still accelerating downwards at 9.8 meters per second squared. So even if you're moving upwards, we still say it's in free fall. So just wanted you to be aware that free fall doesn't only mean going downwards. At this point, I think I should stop and pick it up here on Wednesday, since this deals with how to read position versus time graphs, and it'll be a good review to do on Wednesday. So are there any questions?
I
Yes,
had a
there.
question.
Go ahead. So Eden, I think it is.
Yes. Will there be a quiz on Tuesday, this upcoming Tuesday?
Yes, there will be. It will not be for marks. It's simply for practice and getting familiar with how the crowd mark system works.
Oh, so it's assignment 0.
That's a different thing. Assignment 0 is on Mobius. It's also for practice, also to get familiar with Mobius. Quiz 0 is going to be on CrowdMark.
And will that be posted soon?
Yeah, so in the syllabus, it talks about how the quiz is done. As a heads up, a clarified syllabus discussing the quizzes will be sent around today, and that's something that I believe Samana has done or is going to be doing shortly. So stay tuned for your emails for talking about how quizzes are going to work.
Yes,
Wait,
we
so-
will receive this today.
Is assignment 0 not for marks then?
Assignment 0 is not for marks either.
Is it for completion or like is it just optional?
I mean, like, it's good to do, but if you already know the material, it's optional for you. It's not going to contribute towards your final grade in any way, shape, or form.
Professor, assignment 0 is basically a review of chapter 1 and 2, right?
Mainly chapter 2, and it includes some calculus questions.
Okay, thank you.
Yeah. I should see who's raised their hand. Okay, there we go. Vincent.
Professor, are we going to be given a summary of all the kinematics equations, or is that something we should just make on our own?
That's something that you can make on your own.
Okay.
But I also provided the main kinematic equations within the slides, which you will be able to access.
Okay, thank you.
All right. Thanks, Prof. Bye.
Bye. So Daniel, your hand's raised.
I had a question, though.
Yes.
Yeah, okay, I'll go. Matt, so has assignment 1 been posted yet?
Not yet. That is next Friday.
Okay, thank you.
You're welcome. Okay, I don't hear Daniel.
Thank you, sir. Bye.
Bye. Darsa, is it? Did I pronounce your name correctly?
Yeah, you said it right. My question was for.
Oh, you accidentally muted yourself.
Oh, sorry about that. So for the equations that we learned today, will we ever need to know how to derive them on our own?
Not really. I mean, it's good practice to see where they come about. Tomorrow I'll be talking about what happens when you have non-constant velocity, and you would get similar looking equations. The process is exactly the same as if you had constant velocity.
Okay, thank you.
You're welcome. Nicholas?
Hi, I was just wondering if on the tutorial, our next tutorial, it'll be on chapters 1, 2, and 3, right?
Not on chapter 3, only chapters 1 and 2 with calculus thrown in.
Awesome. All right, thank you.
You're welcome. Max?
Yes, sir. I'm wondering, would you accept like slightly different symbols in the equations during the quizzes or assignments?
We will make sure that all the symbols are consistent. The reason why there were slightly different notation here is because depending on what source you look at, you might see like V initial or V sub naught or V sub naught comma X. They all mean the same thing. This was to get you familiar with that. Even though we might write something in a slightly different way, it doesn't actually change what the equation is meaning.
Yeah, so sorry, I missed a part. So where can we find the standard like symbols you mentioned before?
Look in the textbook. There isn't necessarily a standard symbol database in the sense that with the kinematics equations, I will actually, yeah, with this kinematic equation, we have V naught sub y. Some people might write that as V initial sub y. Some people might also write that as just V initial, or maybe just V naught. So
okay.
The best way to become comfortable with that is to know what the equation is saying and to read through your textbooks, do practice problems. So when you see a symbol that looks like this, even though you might not immediately recognize it, you see, okay, it looks like this equation for kinematics. So I know that this symbol has to be velocity in the initial velocity in the y direction.
Okay, so you mean as long as the symbol makes sense?
Yeah, yeah.
Okay.
Another thing that really helps is when we give assignment problems, quiz problems, test problems, what we would say is an airplane is traveling with initial velocity v naught in the northward direction, and person is on the ground at a distance D equals 21,000 feet below the airplane. So we'd actually provide you with the definition of each symbol within the problem.
Okay, thank you, sir.
You're welcome. Hold on one moment, I lost connection. There we go. I'm not sure if someone asked a question, so
Matthew,
Hassan,
another
did I say
question.
that correctly?
Yes, you did. I just have a question. So for the, I don't know.
Oh, sorry, I still wasn't connected. I lost headphone
Okay,
connection.
no problem. Can you hear me now?
Yep.
All right, perfect. I don't know if this has been asked. I just can't find the due date for the introductory assignments. Do those have a due date, or are those like we do whenever we can?
Do whenever you can. It's purely for your practice. The introductory assignments have no due date.
Okay, perfect.
Assignment 1 is going to be the first one that will have a due date, and that will be indicated directly on assignment 1.
Great, thank you so much.
You're welcome.
What will be on assignment 1?
Kinematics. It'll be kinematics in 1 dimension, 2 dimensions, and 3 dimensions. 3 dimensions is the subject of chapter 4. It's essentially doing 1 dimension, but in 3 different ways. In the X direction, Y direction, and Z direction.
So are we supposed to finish up chapter 3 by ourselves over the weekend, or
Nope,
no?
I'll be talking about the rest of chapter 3 on Wednesday.
Okay.
Yep.
And so what are the tutorials for?
Tutorials are for practice problems. This upcoming tutorial will deal with the math review.
So where can we find problems to work on?
You can find problems in the back of your textbook. You can also, in the websites I'll be posting on Learn, I think they might have practice problems as well.
Okay, so I have